Hey, hello everybody. Dr. Metis here, coming to you today, talked about the periodic table. Lately, we've been talking about atoms and electrons and such things, but right now I just want to say, what is the periodic table? Just a little bit of the history of it. It's a cool little story. The periodic table is this big layout of all the elements, and the more you dig into it, the more cool it is, just the way that everything is arranged and how it totally mimics the atom. But for right now, I just want to say, look, this is how it came into being. Already. The periodic table dates back to 1869. It was created, discovered, whatever you want to say, put together by a Russian named Dmitry Mendeleev, who has a great little history all of itself if you want to investigate that. Already. But back in Mendeleev's time, it did not look anywhere like it looks today. Those were the only known elements that were known to Mendeleev. All right, fraction of what we have today. And he didn't arrange his periodic table to look like that. Okay, it looked differently, but I'm trying to put it in context of what we know our groovy periodic table. In Mendeleev's day, you had about 50 some odd, maybe 60 atoms that had been, elements, I should say, that had been discovered. He sat down and it took him like 3 days. He likened it to organizing cards in solitaire and just organized the elements. But let's go back a little bit and just say, hey, you had on brainers, okay? He got these triads. He did some in like 1817. In a couple years, he created more. The one I did not put in was iron, cobalt, nickel because I didn't feel really comfortable because it's going left to right. I want to stick with the families that go up and down. But Dobereiner said was that he had these triads, and these elements he put together as little groups just because they were known to behave similarly, so they thought they might be related. And he found it interesting that the middle element, if you arrange them by atomic mass, thanks to John Dalton, the middle element pretty much had the average atomic mass of the other two, so there's definitely a pattern going on there. Okay, but that's pretty much where he left it. All right. If you go ahead to 1865, John Newlands proposed a law of octaves. It kind of didn't really, most people didn't like it. He basically likened it to the keys in the piano, hence the word octave. He said, hey, in groups of 8, the pattern tend to repeat itself. All right, so if we go back up here, basically you have 1, 2, 3, 4, 5, 6, 7 would have been missing, but chlorine would have been 7. Down the next one, 8. Like at factor of 8, every octave, the thing's repeated, like, key C repeats in the piano, key C. That same pattern kept finding itself out. People didn't really dig it very much. Okay, but then, no, seriously, 1869, just 4 years later, Mendeleev put forth his atomic table, which incorporates some of that, and everybody thought it was just the best thing. Mendeleev based his table on increasing atomic mass and similar properties. And most people only remember increasing atomic mass, okay, because, I don't know, they just like to shorten things, a 10-second snippet. If you only increase the, if you think about playing cards, if you put them in order, that's one thing, okay? But to group them by properties adds another dimension. Like, how do you know when to end? Like, how do you know that, if, where was it? Like when you get down to O right here, how do you know that to come back down here is sodium that you just don't have sodium right there? And the reason is he used those triads of Dobereiner, I'm sure, and grouping them by similar properties force, that, hey, these guys are in one column. Over here, we got other stuff going on. And it sort of ends the table. So you know where one line ends, the next one begins. And sort of how this stuff gets kind of stuffed in the middle because of the properties. All right. And then within that, you organize it by atomic mass. But one of the other little neat things is you have right down here tellurium and iodide. And Mendeleev was smart enough to say, look, tellurium has a greater atomic mass than iodide, 127 to 126.9, okay? But he kept tellurium in that triad, iodide in the other triad, because of similar properties was sort of ruling what he thought about. So that kind of made it a really good table. But he went one step further to make it an excellent table, is these things where there were holes. All right, he named those elements and predicted, like, the density, specific heat values, atomic masses, all these little things about the element. And his predictions turned out to be pretty darn accurate, okay, which is actually really cool. All right, I don't know what this T is there for. That shouldn't be there. All right, so he got to make yourself famous to last 1.5 centuries. You got to do things really well. You don't do it halfway. So he didn't just arrange it by mass. He arranged it by mass and property. Then he did one better and say, hey, where these holes are, let's just say, hey, these elements exist somewhere on the planet. And that's okay. That's like being in a classroom, seeing an empty desk, and estimating exactly who's going to sit there and what they're going to look like. That somebody will sit there. Not that they're never going to sit there. Not that these elements don't exist. He said they do exist. We just haven't found them yet. That's pretty cool. That's pretty neat. Okay. And his things were all right. So anyway, from Mendeleev in 1769 onwards, upwards, we had lots of discoveries that I've talked about in other videos. Mainly, we have this whole idea of the atom that's being discovered, electrons, protons. Okay. Mendeleev didn't have any of that there. They only had atomic mass. But Henry Moseley took advantage of that. In 1914, he reorganized the table, so to speak. He arranged it not by atomic mass, but by atomic number, which kept the order the same, but he proved that it was based upon atomic number, that these properties are repeating because of the protons in the nucleus. And he stated that down here, chemical and physical properties of elements are functions of increasing atomic number. So far, every new element that gets discovered, and we just had like 4 new elements come out like a year ago, finish off that last row, okay, maybe 2 years ago. Iodine follows Te, not because of properties, just, no exceptions. Iodine's atomic number is one more than Te, which is why it follows it. That simple. Alrighty. One guy I'd like to mention before I'm done with this thing, Glenn Seaborg. I don't think I mentioned a bunch. Glenn Seaborg lived throughout the 20th century. He died in 1999, and he just was part of, at least, discovery of at least like 10 elements. One of them, technetium, which is widely used in medicine. All right. Seaborgium is named after him. So he did a lot of good for the periodic table. And if you wonder why the F block is pulled out of the periodic table, the lanthanide and actinide series, that's Glenn Seaborg when he was a young and up and coming scientist. He pulled those out thinking that, hey, they're not exactly the same. They need to be pulled out of the body of the table. Also proved to be correct. Our present layout of the table, I'll end with this. You have groups and families. Groups and families go up and down. Like I always go this way. Group, period, goes across. Family can make the other Scrabble piece. And I know you could write the other way, but if it helps you, it helps you. Groups and families go up and down. Periods go across. They have groupy little names like alkali, alkaline, earth. If you ever want to know the difference to memorize them, alkali is one word. Alkaline earth is 2 words. So group 1 is alkali, group 2 alkaline earth. The staircase here represents the division between metals and nonmetals. And just like with peoples, people that are on the borders between 2 countries tend to have, cultures that reflect both countries. They have influences of both. Well, elements that are on the staircase, that have a full edge on the staircase, not just a corner, those elements, they're semi-metals. They have properties of both metals and nonmetals. But for the most part, most of the table's full of metals, a little bit of nonmetals to the right. I didn't scale it right because I had it right in there. You got your noble gases and your halogens, which are some big, widely known families. And down here, I'll leave you with Glenn Seaborg's F block that he pulled out of the table. All right, well, that's it for the basic layout and background of the periodic table. Hope you like it. Take care.